Okay, so welcome to the Demonstrating Implementation Excellence stream at the SNOMED CT Expo 2024. Thank you to FAST for sponsoring this stream. My name is Ian Green, and I'm the Customer Relations Lead for Europe and also the Global Clinical Engagement Lead at SNOMED International, and I'll be moderating today's session. All questions will be answered at the conclusion of the presentation. For online attendees, please use the Q&A button to type your questions to the presenter. And on-site attendees, please use the microphone provided in the room. I'm now pleased to introduce Linda Bird from Bellburn Enterprises. And here we go. Te Kahu.
Te Kahu.
Ah, well, it's as close as you're going to get. There's the Cancer Control Agency in New Zealand who will be presenting cancer data interoperability in New Zealand with SNOMED CT and FHIR. So Linda, please go ahead.
Good afternoon, everyone. My presentation today, as Ian said, is about using SNOMED CT with FHIR for interoperability of cancer data in New Zealand. Before I begin, I'd like to briefly explain my current affiliations. I am the Principal Consultant at Bellburn Enterprises, where I offer SNOMED CT, information modelling and e-health interoperability consulting. I'm an advisor to Canada Health Infoway, an adjunct assistant professor at University of Victoria in Canada, an author of a yet-to-be-published book on SNOMED CT with Springer, and the SNOMED CT implementation lead for Te Kahu, the Cancer Control Agency in New Zealand. And it's in that capacity that I'll be speaking to you today. So I'm going to start with an overview of the CanShare project, what's been achieved so far, and then I'll explain how we've achieved it through the lens of 5 CanShare desiderata. You've heard of the SNOMED desiderata, these are the CanShare desiderata. These are the needs or requirements of the CanShare project. And the project needs clinician-friendly terms, patient-centered interoperability, efficient user interfaces, fast response to change, and manageable maintenance. And you'll see these on the CanShare wheel over to the left. But we're going to start at the center of the CanShare wheel with an overview. And firstly, the main goals of the CanShare project are to enable the collection and timely sharing of relevant and accurate cancer data, to join the many disparate data silos together, to support clinical and patient decision-making at the time and point of care, but also to support advanced data analytics capabilities and to monitor cancer care around the Motu, which are the islands that make up New Zealand. One more thing, in order to achieve these goals, the CanShare project uses 3 main standards. It uses its Logical Information Model, or LIM, SNOMED CT, and FHIR. This is a high-level overview of the CanShare platform, showing data being shared and viewed by a range of participants across the healthcare sector, from primary care to radiology, pathology, radiation, systemic anti-cancer therapy, surgery, multidisciplinary meetings. We also have a number of cancer registers and screening, national screening registers. We have the patient themselves and the data analysts and the researchers. And at the centre of all this is the CanShare platform, which is supported by the New Zealand Health Terminology Service, which is an Ontoserver instance that we call the NZHTS. So what's been achieved so far? Well, we have developed a wide range of CanShare standards artifacts, which I'll talk about soon. We have one of our vendors, Valencia, has developed a native implementation of the CanShare standards in their e-prescribing system. We have demonstrated the operational principles of CanShare in a proof of concept implementation, and we have an undertaking from the New Zealand Minister of Health to require CanShare standards for all new cancer software deployments in New Zealand. So I'm now going to briefly talk about each of these. Starting with the native implementation of the CanShare standards by a company called Valencia. Valencia have developed and deployed a haematology and oncology e-prescribing system in the northern regions of New Zealand's North Islands. The primary goals of this implementation were to improve clinical safety, data availability, and end-to-end efficiency in patient treatment. And as a result of their deployment, users have reported that it's easier to share care within the region. Here is a screenshot of the Valencia RORO system. The oncologists first enter the diagnosis data through a series of fields, including the cancer service, the cancer stream, the substream, the type, the primary site or location in the body, the laterality, and the histology. This data is entered natively using SNOMED CT, and then when it comes time to sharing the data, the codes and terms are collected together into a FHIR bundle for sharing. And the same occurs for staging, prognostic factors, and grading of the cancer. The data is collected natively using SNOMED CT and then shared using FHIR. And lastly, the medications are prescribed, the cancer regimens. They are collected using SNOMED and shared using FHIR. This e-prescribing system developed by Valencia benefits thousands of patients across the northern part of New Zealand. And as explained in this article, the system was designed using SNOMED CT for data capture and FHIR for data exchange, making it the first CanShare standard system in New Zealand. At the same time, the team, in collaboration with Health New Zealand, developed a proof of concept system to demonstrate the data flow of data from the RORO system to a FHIR server that collected and validated the FHIR bundles and displayed them on a proof of concept dashboard. And there's just a couple of screenshots of this dashboard. So let's come back to the CanShare desiderata. These are the requirements of a successful CanShare system. And we're going to step through each of these and talk about how we have achieved these. Starting with clinician-friendly terms. The first requirement on the CanShare wheel is clinician-friendly terms. Now, to support this, the team's worked with over 200 clinicians from specialist pathologists to hematologists, medical oncologists, pharmacists, radiation oncologists, and many more to select a CanShare preferred term for each of the concepts in the CanShare value sets. And we start with a simple spreadsheet and work with the group of clinicians that represents the source of truth of the particular type of data that we're collecting. The CanShare preferred term represents the interface term that implementers use on the display, and we store this preferred term in the context, the CanShare context language ref set. Get me a drink of water. Thank you. Once we have selected the interface term or the CanShare preferred term, we use the SNOMED International Managed Service to define the CanShare dialect preferences. And as I said, these get stored in the CanShare language ref set. At the moment, we have over 4,500 interface terms in the CanShare language reference set. And when implementers want to retrieve the CanShare value set, they execute a $expand operation on the value set with the display language set to this value, which uses the concept ID of the CanShare language reference set. Thank you, that's much better. And just a tip, if you're developing interface terms for a system, you sometimes need to use value set specific interface terms. So a classic example of this is where you're wanting to represent the other value, that catch-all last value in a value set. Here is a simple example of a value set where we have two types of lung cancer followed by the term other lung primary. Now, rather than creating a new concept for other lung primary, which would be bad practice because the meaning of other lung primary can change depending on what value set it's linked to, the solution that we use is to define a FHIR value set with the first two values for lung non-small cell carcinoma primary and lung small cell carcinoma primary using an ECL, and these inherit the default CanShare interface terms or preferred terms. And then that third term, we bind to the generic lung primary concept, which is the parent of the other two, and we override the preferred term with the display term of other lung primary. And that allows us to bind to the correct concept, but also show the correct interface term. So spinning the CanShare wheel to the next CanShare requirement, patient-centered interoperability. So we need to break down the silos of data, but also the silos of data standards to enable the data to flow around the healthcare system between healthcare providers to support the patient's healthcare journey, from clinical investigations to clinical assessments, pathology investigations, multidisciplinary meetings, primary care, cancer diagnoses, and treatments. And the way that we do this is to define a logical information model, or LIM, with consistent SNOMED CT bindings. But what did we do before we had the LIM? Well, we had a whole range of data standards which were all developed in silos. We had separate standards for pathology requests and reports, systemic anti-cancer therapy, radiation oncology, multidisciplinary meetings, and cancer registers. And each of those were developed separately, and each of those were different. And even within one of those areas, there was a different standard for each cancer stream. So whether it was breast, lung, prostate, colorectal, or hematology, they all had a different standard because they were all developed by the specialist clinician who knew the information requirements for that particular area. So when it came to SNOMED coding the data and planning out how the data was going to be shared across the healthcare system, there was no consistency and it was almost impossible to achieve interoperability. So we introduced the CanShare LIM as a way of representing the information requirements for sharing the cancer data. The LIM defines the data elements, the constraints, and the terminology bindings for each topic. It provides the blueprint for representing data consistently across the projects and cancer streams. We've defined the LIM in a way that's consistent with FHIR, using FHIR data types. And we do this so that we can provide an efficient process for generating the FHIR questionnaires from the LIM. The fundamental building block of the LIM are data groups, and each data group represents a clinical topic. So, for example, a patient or a body site or a specimen, a cancer diagnosis or a mitotic count. Those data groups are then collected and bundled together into a section, which is like the heading on a form. So here are some examples, like the microscopic findings section on a form, and the sections are grouped together into compositions, such as a pathology report for a breast resection. The composition then becomes the source of truth for the data standards, the FHIR questionnaire, and the FHIR implementation guide. So we use the FHIR questionnaire to collect data from the users, and we use the FHIR implementation guide to share the data and the semantics or meaning of the data using FHIR resources. So here's an example of a data group for body site that has a number of data elements, including body structure and laterality, etc. And for each of the data elements that's coded like body structure, we use the FHIR data type codable concept. It's associated with a SNOMED value set like CanShare topography, and it may have a fixed value or a default value. Within the LIM, we're able to use a $expand on the terminology server, the NZHTS, to expand the value set that's bound to that data element so that we can check the values and check the interface terms linked to that data element. And then the data groups are grouped into sections, which are like the headings on a form. Here are two examples, a clinical information section on a colorectal histopathology request and the microscopic findings on a colorectal histopathology report. And you'll notice that there's quite a few data groups all grouped together under the one heading. And then the sections are grouped into compositions, which are like a data entry form. And the compositions are used to generate the FHIR questionnaires. A FHIR questionnaire is basically just a JSON file, but it can be rendered in any standard FHIR questionnaire renderer like this. And this is where the SNOMED data can directly be entered. So on to the next CanShare desiderata, and we've spun the wheel to efficient user interfaces. So this is all about speeding up the data entry process and reducing the effort required for clinicians to enter high quality data so that clinicians can spend more time caring for their patients. So with this in mind, we've designed an approach using SNOMED CT and FHIR to offer context-aware user interfaces. So I'm going to show you a demonstration of the interface and how it works, and then I'll explain the mechanism behind it. Now, this interface uses similar fields to the RORO system I showed you earlier: cancer service, stream, substream, type, primary site laterality, and primary histology. So let's look at the first scenario. In the first scenario, we're going to choose medication oncology, and then genitourinary primary, urinary system primary, kidney primary. Now, the kidney is lateralizable. Notice that the primary site, the body site, got auto-populated from the primary type. Kidney is lateralizable, so we're going to choose left, and then we're going to choose a primary histology of clear cell sarcoma. Now, notice as we move forward through the system, we were only shown values that were relevant based on the data that we'd already entered into the system. So if we clear the screen and try a new scenario, and this time we're going to choose medical oncology, CNS primary, and brain primary, you'll see that the values presented to the user are different based on the context of what has been entered. Now, when we get to the brain is not lateralizable because we only have one of them, but it does cross the midline. So for body structures that cross the midline, we allow users to select a side. It can either be left side, right side, both sides, or central. So using the same principle as the lateralizable body structure ref set, we maintain a reference set of body structures that cross the midline that can have a side applied to them. Now, this is really important for treatment areas like radiation oncology, where not just the laterality, but the side is also extremely important for clinical safety. So in this case, we're going to choose right side and glioma. Now, the clinicians love the fact that the values dynamically adjust based on the values that they've already entered, and that the system auto-populates based on any values that can be auto-populated. But sometimes they just want to go straight to the cancer type, or they just want to go straight to the histology. So that's where the reverse engine comes in. So we're going to refresh the form again, and this time we're going to go straight down to primary histology. And we are going to enter acute myocytic leukemia. And when we do, you'll notice that because there's only one cancer type that this histology belongs to, the first four fields automatically populate, which makes it really fast for the clinician to enter data. If we try again, and this time we enter renal cell carcinoma with fibromatous stroma, we'll see that the first 5 fields auto-populate, and we just need to choose a laterality. So these context-aware user interfaces allow the clinician to start anywhere on the form, and the reverse engine will populate backwards and the forward engine will populate forward. Now, we drive these engines using a combination of SNOMED CT and FHIR, FHIR concept maps. This is the UML for FHIR concept maps in release 4, and we use the source element, the target element, and the depends on elements. Now, the source element is an observable entity that represents the field on the form that the user wants to enter data into. The target element represents the value set that they should use to enter data, and the depends on represent the data entered into the previous values. Now, this system is currently implemented in Valencia's UAT system and is scheduled for deployment by the end of the year. We provide it for all of our vendors on the NZHTS for them all to deploy. And the phase 2 concept maps will include displaying the grading, staging, and prognostic factors given the histology and topography entered. And this is the JSON of the concept map that we publish onto the New Zealand Health Terminology server to make that available for vendors to use. On to the next desiderata, on to the next requirement. So we've spun the wheel to fast response to change. Now, we want our vendors to use the value sets that are published on the terminology service. However, the New Zealand edition is currently only published every 6 months. But even if it was published more often, we would still need a pragmatic way to be responsive to implementation, feedback, and requirements in between those publications. Feedback can range from enhancement suggestions through to critical clinical safety issues. We need to be able to add new concepts, update display terms, and update value sets. And we need to be responsive because clinical safety issues just can't wait for the next SNOMED CT release. So our solution is to leverage the flexibility of FHIR while rolling the changes into the next SNOMED release. So for example, in October of 1 year, our 5 value sets might align with our SNOMED CT edition. And then in between the releases, we might need to add some codes, remove a code, and then we roll those changes into the next SNOMED release. During the next release cycle, we may need to change a display term, and then we roll those changes into the October edition. So in order to achieve this, we use a technique we call hot fixes. So this is an extract of a value set definition in FHIR, which uses the ECL query language to define the members of this value set as being the members of the New Zealand cancer type reference set. If we need to apply a hotfix in between releases to change a display term, what we need to do is minus that concept from the ECL and add it back in with the overridden display term. If we need to remove a concept from a value set in between a release cycle, we simply minus it from the ECL. And if we need to add a new concept to a value set that's already been published, we can simply do an OR as long as we have a CanShare dialect preference on interface term on that concept. However, if we need to publish or add a concept that has not yet been published on the terminology server, we need a way of adding that concept and making it available on the terminology server. So to do that, we create a code system called SNOMED Unpublished, and we temporarily add that concept into that code system as a pre-release process. We author it in the authoring tool, add it temporarily, and then in the next release that gets published as part of the formal SNOMED release. Now, there is some risk to this, but implementations and clinical safety just can't wait 6 months for the next SNOMED release. So, spinning the wheel to the last CanShare requirement, managing maintenance. Now, maintenance is an essential part of any project like this, but one that's often not deliberately planned for. There are many aspects to maintenance, but I'll just cover these two. Maintaining data standards. Well, because we're using the logical information model and data groups are reused across our different forms and compositions, that leads to less redundancy. So typically, if we want to make a change, we can make it in one place and that rolls across. We do have a mechanism for versioning to create stability, but it allows us an easy way for maintaining and making changes. In terms of terminology standards, we use the RefSet tools versioning maintenance mechanism to migrate inactive codes using the historical suggestions. We've got a library of ECL queries to identify when changes are required to the CanShare dialect, and we use a web-based tool to manage the validation and updates to the value sets and concept maps. So in conclusion, New Zealand's CanShare project demonstrates the use of SNOMED CT with FHIR to enable clinician-friendly terms, patient-centered interoperability, efficient user interfaces, fast response to change, and manageable maintenance. But really what this is all about is delivering effective solutions to supporting the care of cancer patients in New Zealand. This is my email address, linda@bellbirdinformatics.com. Please feel free to email me or ask me questions now. Thank you.
So I'll do that again. So thank you, Linda. We'll now take question or question. As a reminder, so if you're in the room, please use the microphone. I don't have any questions online. So do we have any questions within the room? Okay, I'll give you one question then. How did clinical users respond to using SNOMED CT in the user interface?
I think some of them were hesitant at first, but because they were actively part of the process of designing the interface terms, they really engaged in that. And they also really appreciated this improved speed and efficiency of the data entry processes by guiding and reducing the value sets that they were given and giving them context-aware user interfaces. They really appreciated more efficient user interfaces. Faster data entry is always looked on kindly by busy clinicians. So very keen. They certainly helped us encourage the vendor to implement both the interface terms and the concept maps, which was wonderful. Clinician-driven and encouraged. Mm-hmm.
Excellent. I'm glad to hear it. Thank you, Linda. Oh, hang on. Go on. We'll do it quick. You got a microphone coming behind you.
Excellent. I think this is a very good learning that we can bring home. My question is that, can you explain more the process that you can get the interface term from the specialist? How would you do that? Get the conference, let them together, let they see the sample of the questionnaire or something like that. How to get they agree on this? This is the interface term that they are happy with. And how about the acronym, something like that? How you dealing with those?
So yes, it's always a challenge. We followed the principle that the clinicians who were the source of truth of the data should have the say. So if it was histology data, we started at the pathologists for that particular specialty stream. We found a representative set of pathologists, and then we did reviews of the interface terms in the clinical user interfaces that had been selected by their peers. So it was very much a case of who is the origin of the data, and then getting review afterwards. But there's always situations where you get disagreement on that need to be resolved, and then we get groups together and lock them in a room, and typically there is someone who's most senior who makes the final decision. No, no, please don't. That's recorded, isn't it? No, we didn't.
Okay, so thank you, Linda. With that, I'm going to conclude this block of sessions. Please join us tomorrow at the James Reed Memorial Lecture, which is at 9 o'clock Korean Standard Time. For those of you on site, please join us now in the exhibition hall for the networking reception, and don't forget to play your passport game. Thank you.